Good evening, everyone, and thank you for joining this today's webinar on RTL design and automated verification, a practical based Verilog webinar. Today, we will try to understand not just Verilog syntaxes, but how basically the professional VLSI people, engineers, and the semiconductor industry people are actually designing the hardware, and they are verifying it before manufacturing, right? So many of the engineers at the beginner they may think that Verilog is a kind of you can say the language like a C and the Python. So sorry for them, right? Verilog is a kind of a language which is describing the hardware, not the software, right? Whenever you write a Verilog program, it is actually the main aim of that is actually to design an electronic circuit, which maybe later on can be, you can say, converted into the chip by simply, you can say, the implementing the billions of the transistor on that particular one, right? So you can just simply take one example. Let's say there is a mobile phone which is you having. There are the processors in that which are simply handling the cameras. They are handling the graphics, the memory, the communication between the protocols, between the you can say the peripheral devices to the processor, right? So every one of these processor which I'm just talking about, they just started their journey from the RTL code even, and that might be written in the Verilog or the system Verilog, right? So in today's session, what we aims to be that we will try to get what exactly the RTL really means to be, and how Verilog is basically used to model the hardware, how to write the simple designs, and how to simulate them, and how verification of these particular duties can be done by using the Verilog. And definitely you will get some you can say the insights on the industry workflow, that how industry is working to verify the particular hardware before it's going for the manufacturing, right? So I'll just start it with my introduction. So this is Sanjay Kumar Seni. Actually, I'm the knowledge associate in future future right? Basically responsible for the academic, you can say the delivery to the students who are willing to enter into the VLSI domain, right? So let's come here. So I'll start my session with the that what exactly the RTL design, and what exactly the VLSI flow is, right? So every semiconductor chip, if I'm just talking about this, follows some standard design flow, right? Means they are going from the you can say the basic to the until the chip is not coming in our hand. They have to follow some standard design flow, right? Think, let's say I'm just constructing a building, right? So you really you will never going to start that the placing the bricks on the you can say the land, right? It has to be first come with the requirements, that how many room size, how many rooms, how many you can say the bedrooms you required, the guest rooms you required, and exactly I mean to say the infrastructure, that what exactly you require. Then you need to go with the architecture, then you will find the blueprint of that, and then the constructions will be there, and then at every point of the time the inspection will be there. The same flow, the same thing is happening with the chip design, that is also having the following stages. So let's say I'll just talk about the specification first. And the specification is basically the customer request, that what kind of the product he wants, right? So if I'm just talking about the specification, let's say some customer is saying that I need some kind of the processor which is just simply supporting the PCI, the peripheral ICs with the low power, right? So this is the specification which is given by the customer, right? And then it will be simply converted that into the functional block by using the digital system design. We are just converting them into the, we are describing the functionality of that basically, and then it will be coming to the RTL design. Now in RTL design, what RTL engineers are doing, they are converting this specification into the very low codes. Means ultimately whatever the circuit you have thought about, whatever the you can say the chip you have thought about, that is converted into the soft form by using the very low. The simple example, let's say a customer wants that if is a signal is selected, once means let's say I'm just talking about a customer is simply want that there are the two signals and these will be selected at some instant and this will be selected at some instant, right? So the RTL engineer, the design engineer may write a mux which is simply having the two inputs, and they can take it as the selection line, right? If it is 0, then A will be selected, it will be going to the output, and if it is 1, then B will be selected and going to the output. So this is basically the requirement of the customer, and RTR engineer is doing what? It is just simply converting this specification into the soft form by writing the you can say the Verilog code for this particular design, right? And then, as I told you, given you the example of building a home, that after every stage there is a inspection is needed, that whether we are going into the right direction or not, because once the home is completely built, then it is if we are breaking any kind of the wall, removing the rooms from there, then it is a wastage of the money, wastage of the power, manpower, and definitely the wastage of you can say the time as well as, right? So the functional verification is very very important after each and every step, right? So before manufacturing, the functionality of that will be verified, that I which the code which I return, the RTL, is it working perfectly or fine and as per the customer requested or not, right? And this basically the functional verification. If I'm just talking about the complete design flow of a chip, almost 70 to 80%, you can say the project time will be, you can say the consumed by the functional verification, right? And that functional verification manually it is never be possible, right? Because ultimately thousand of the test cases you have to apply in any kind of DUT to just verify its functionality, right? So some automated kind of the structure we have to create. In that, automatically it will be taking the test benches, test cases, right? Applying to the DUT, capturing it automatically. It is you can say comparing with the expected result and giving that whether the test case is pass or fail, right? That is the really you can say the industry people are working on that by creating the test benches, right? So for that purpose here, the system Verilog is playing a very very important role, right? It's a kind of you can say the HDVL, that is hardware description as well as the Verilog language. And if I'm just talking about the Verilog one, so this is the HDL, the hardware description language, which is just used to create or describe your hardware. And by using the SV test benches, we are just simply verifying our DUT which we have written, right? Then it will come to the synthesis one. In the synthesis one, this RTL code is converting into the gate level netlist. Means simply by using the gates, by using the FFs, flip flops, by using the buffer, we are simply representing that particular circuit or that particular chip in form of the blueprint. Basically, you can relate with that example, and then it will be sent to the PD department. PD, you can say physical design, right? Now, what they people will do, they will simply you can say the gates or the flip flops or the buffers which we have just used, they have to they will generally look these gates and the flip flop at the transistor point of view, that how many transistor are going to be used to make that particular circuit. So in this PD you can say flow, that it will be going through the routing process, placement process. They are simply doing the clock synchronization, so clock tree is there, and definitely power optimization is going to be checked here. So again it has to go through the verification, you can say the uh, step, that complete PD what where which component is basically going to be placed, so that is going to be verified. And then furthermore, if it is uh, functionally correct, physically it is correct, then it will send to the fabrication team where the chip is going to be manufactured. And then whatever the silicon that will be there on in our hand, that is going to be tested again. And now if it is bug free, then it has to be sent to the, you can say the team which is simply assembling and is assembling in the devices, and we people are enjoying that technology, right? Now let's assume that at the final manufacturing, let's say if we are testing the silicon, and at that time we are finding some bug, right? So it is very expensive, my dear all, and sometimes it is a loss of millions of the dollar, right? So we have to be very careful by verifying the, you can say, at early stages, at each stages, if we are talking about, once we have defined it in, you can say, soft form by using the RTL. So where we are doing the verification here, some bugs has to be free, means it should be bug free. Then again, in the PD also we are simply verifying that, so that is also be bug free, right? So this is the complete VLSI design flow that every semiconductor industries, or any you can say the intellectual people who are responsible for throwing the chip in the market, they will generally flow this standard design, right? So now let's come to the understanding of the RTL and introduction to the Verilog HDL, right? As I already told you, the register transfer level is the term RTL. So let's break it into the three part. One is to be as register, right? Another is to be transfer, and the third one is to be the level, right? So registers basically for the storage of the data, and transfer means from one register to another register we have to send the values, right? And we have to control the, you can say, the flow of that data, right? You can imagine, I'm just giving you a practical terminology related to that. So let's say I have some water tank which are connected with multiple pipes, connected with multiple pipes, is the perfect example of that RTL, right? So here, water tank is basically the register, and whatever the pipes you are using, they are basically the transfer levels, that where the data, where the water is basically flowing. And by using the clock, right? In case of the clock, you can say, decide the water moves, right? So in case of the RTL, basically the data moves on every, you can say, the clock edge, right? That they are flowing from this register to this register, right, for the synchronization purpose. Right now you can just see the basic concept of writing the very low code. So it is a IEEE standard HDL, right? Every code has to be started with the module keyword, and it has to be ended with the and module, right? As this complete webinar is based on the RTL design, and you can say the automated verification. So I hope all the participants who are joining this webinar, they have the little bit understanding of the very low code. They have done some basic level of the code, right? So if you see the code structure, it has to be written between module and module. Then you will be simply writing the identifier or the name of the module, right? In that we are simply defining the ports, that how many ports, how many variables I required, and how they are behaving, either they are working for the input or the output. And then we are simply writing the logic for that. So here we are using the behavioral style of the modeling. This always is a kind of procedural block. So, and this at the rate is the event control directive. We are giving the sensitivity list here as this circuit, which this code is defining, that is the multiplexer. It's a kind of combinational circuit. So in the sensitivity list, all the inputs must be there, on which the output is depending, right? So by default it will take A, B, and selection line as the sensitivity list, and then we are simply describing the behavior of that if selection line is equals to 1, then y will be coming as B. If selection line is equals to 0, means else part, then y is getting the signal A, right? So this is the complete, you can say, the flow of writing the DUT in very low. Some basic example I just have taken over here. So you have some key, you can say, data types, you can just see. So it is a wire that is basically representing the continuous signals, right? Reg is a kind of, you can say, the data type which is simply having the storage element. Then the operators we can use just to define the always is basically a procedural block. At the rate is event control directive, which is simply hold the simulation until there is a change in the sensitivity list, right? So this is a basic standard, or you can say the steps that you have to follow while describing any kind of the hardware by using the uh, Verilog HDL, right? Same here. I just given the demo for 2x1 multiplexer. So the same code is written over here, and they have just told about the always, and the, you can say, some blocks are there, some you can say the rules you have to follow, that in behavioral style of the modeling, the output which you are defining, that must be of your edge type always, right? You need to, if you are using the case, so you should use the default, right, to prevent that particular condition from the latch inferring, right? So I hope you everyone is familiar about that, right? Now let's see, if you are if you have already written your RTL code, then we do not need to send that to directly for the manufacturing of the chip. First we have to just simulate this, right? And we like we can take an example, like let's say we are just simply testing a car inside a virtual environment, right? So it will be not be a harmful. We should not take a physical card and car and going with the, you can say, the hit to just check that whether your airbags are working or not. We have to take that car into the virtual environment, and we have to uh, observe, right? We have to check whether it is perfectly fine, the safety features are perfectly fine or not, right? So there are some steps you need to follow here. In that, first step is coming as the compilation. It will just simply check the syntax error, right? The code which you have written, whether it is syntactically correct or not, right? For the means ultimately it is the checking the grammar in the English, right? That whether you have used the correct grammar, whether you have used the correct rules and the regulations, right, which is making that particular DUT synthesizable, means that can be converted into the hardware, right? Once it is done, then it will just go with the elaborate. Elaborate is simply doing the connecting of the all the modules, connecting of all modules. Means it is not necessary that the DUT which you have written, that is having a complete big block. It might be happening that the complete module is subdivided into the small structures, so you have to connect them all, right? Either you can just do it like this way, that one module is for the DUT, another module is for the test bench, so you have to connect the variables of them to just send the appropriate set of the input to the appropriate inputs of DUT, right? So that will come into the elaborate reason, where we are connecting all the modules, and then it will go with the simulation, right? So here all the inputs are applied inputs applied, and we are just simply generating the outputs, right? So that is simply to be known as the simulation, and then we are just simply analyzing the waveform. So here it is a kind of you can say the output, capturing the inputs as well as output in terms of waveform, right? So the perfect example over here, it is a kind of like the checking the heartbeat by using the ECG report. A very good example over here. Instead of observing the signal on the digital basis, we have to just go with the ECG, and we are getting some signal in terms of the signals. So by that we can just check the condition of the heart, right? So this is the perfect uh, steps through which it has to go after going with the after written the RTL code before manufacturing, right? Then it will go with the functional verification. As I told you, the 60 to 70% of total chip design is basically depend upon the verification, right? The efforts of verification, right? If a single bug is coming in the silicon, you can say the product which you have implemented, they may give you the loss of, you can say, cost of millions of rupees, right? So verification ensure that whatever the RTL you have implemented, is it matched with your required specification, or it is committed to the fabrication or not, right? Now design, if we are talking about the verification, so there may be two kinds of a bug. Let's say first one, I'm just talking about the design bug. Design bug means it might be happening that RTL which you have wrote, that is wrong, and the test bench which you have wrote, that is correct. So definitely, if the logic which you have developed it is wrong, then definitely it will give you the wrong result. In verification, it might be happening that the RTL which you have written, that is perfect, but the test bench you are writing, that is wrong, right? So that you should know. The you can say the analogy for that. Let's say a student and teacher, right? Let's say a teacher is evaluating a seat of the student, but teacher is having wrong answer key, wrong answer key of the test. So definitely it will be wrong, it will be wrongly checked, wrongly evaluated. So the test case, the student may get fails, right? So on behalf of that, if any design bug or the verification bug is there, they will be simply giving you the test case pass or fail. Pass means the whatever the test case you have applied on that, your duty is perfectly fine, it is giving the expected result. And if it is not giving, then the test case will remain the fail, right? So in the industry reality, if we are talking about, so they are basically working on the automatically compare based, automatically compare means it is not happening that every test cases have to give manually, and manually you are checking that whether it is correct or not, right? So that's why the automated verification, or you can say the test benches, are required to just verify your duty, which is just simply working like a scoreboard, right? In a scoreboard, it is just giving that how many test cases are passed, how many test cases are failed, by simply checking them uh, with the expected result. Means whatever the result you got it from the DUT, they will be checked with the result which you are expecting, and according to that it will give you the test case pass or fail, right? Now if we are making the test bench architecture or the self-checking test bench, so we have to just work on some modules. The first one is stimulus generator, which is just simply generating generating the different set of input set of input, right? And that will be derived to the duty. Once it is derived to the duty, then monitor is observing the output signal, so it is just capturing the input and output with respect to these inputs, right? Then a scoreboard is basically checking, means comparing that whether the test case is fail or pass, right? Means did you get the expected outcomes on the respective test cases or not, right? It will just simply generate you can say the summary that how many test cases are fail, how many test cases are pass, and they all uh, has to be drive and just to verify this hardware, which is to be called as design under test, right? So if I'm just talking about the Verilog, sorry, industry level verification, right? So they will be working on these levels only. First, they are writing the RTL code, means just describe the hardware. Then they are creating the test bench through which it is driving. By the test benches we are driving the set of the input to the RTL code and capturing the input and output. Then we are just simply doing the simulation, means same, we are just generating the you can say capturing the input and output, and then we are adding some component which are automatically checking that whether we are getting the correct result or not. And if some bug is there, we have to inject and fix that bug, and then we have to start the process from starting again. Once it is all the test cases which you have applied, they are passed, then it will be sent to the you can say the PD department, right? PD, you can say the flow it will be going, right? So if we are talking about industry verification and flow of the common RTL verification, so first RTL development done, test bench creation done. Now assertion is something like a CCTV, right? It is continuously observing your test cases, or you can say the test bench. Wherever there is an error, right, it will just promptly uh, acknowledge you. Yes, we are finding some mistake over here, we are just finding some you can say the bug over here. Means it's simply trigger the alarm whenever some unusual activity will be there. Alarm is going to be triggered, right? Then functional coverage is something, let's say I just have 100 of the test cases, and out of them 70 test cases we are just getting is at pass, so it means 70% coverage. We can just say that it is successfully. So in the industry we always try to get some kind of the verification. By using the verification we'll try to get that in the duty the coverage must be more than 90%, right? And then regression testing means the thousand of the test cases have to executed automatically in the night, right? And the morning engineers will check the reports only. It is not happening that you have to sit manually and you are watching that how many uh, you can say test cases are passed, either we are getting it as a result as pass or fail, right? So regression will generally is a kind of automatic process, right? It is a night process, and in the morning what they will do, they will simply check the result, that how many test cases are applied, and out of that what exactly the summary is, right? How many are passed and how many are fail. Now if you got that 20 test cases are fail, then they will be gone with the debugging, and once it is completely verified, then it will be sent to the sign off from the front end team, right? These are the basic mistake during writing the code they can do: blocking, non-blocking assignment, incomplete sensitivity list. We have just taken the example over here. Let's say I'm just not putting the selection line in the sensitivity list. So input is not only dependent upon A and B, it is also dependent upon selection line. So definitely it will give you the error. Latch inferring, let's say I'm not giving the default statement in the case, so definitely the last given the test cases according to the result will be there. So it will create the problem of the latch inferring. Raise conditions you should know, right? So these are the some common mistakes can be done by the engineers while writing the RTL code, right? So now, before going to the career and the roadmap, I would like to take you people to one, you can say the live code, right? That how exactly the people are looking at the code, how they are writing the DUT, and how they are developing the automatic test case, right? So I'm just taking one scenario over here. Let me add one slide so we can come to that. Uh, Here only, I'm just adding one more new slide over here, right? So I'm just telling you the specification of the customer, that let's say I have to make a 4-bit comparator circuit, comparator circuit, which is having two 4-bit number. One is A and B, both are 4-bit, right? And it is comparing these number and giving the four outcome. One is either it is greater, either it is less, or either it is equal, right? On that behalf of that, it should be given. So we have to just write one DUT. This complete will become a part of the DUT, and we have to write one test bench to verify this particular hardware which is just making this. So to make it automated, what are the components that will require? So first, everyone knows that you have to start your code with the module. Then you will just instantiate the DUT, means the connection of the variables which you are taken over here, they will be connected to the variables of A and B, greater than, less than, or equal. Then to create the automatic test bench, let's say first one is we have to take some, write some task to apply the input, to apply the input. Then second one, the important one, we have to display, task to display the test, that what values we are going to be printed. So display test we required. Third is we have to check the result. So one task is to be written to check the result, check the result. Fourth one, we have to write one task which is a task to just run a single test case, run a single test case, right? And then we have to just do the random test cases we are just writing. So one more task has to be written for the random test, and then we in the end we are just simply you can say printing the summary, that whether we are getting the correct result or not. So just note these all components of the automated based test bench. So one duty has to be written, which is simply describing your hardware, and we have to write one test bench, which is having these you can say the many components. First, we are taking the input, then we are displaying the test, we are checking the result and comparing them. Then one single test case is to be passed to them, and then we will just apply the regression in that. Random values will be generated, they will be passed to the dut, and it is just simply capturing the summary of that, right? So let's do write the dut first. We are just specification, we got it, means what kind of the hardware we require. So we directly go on the tool, and first we will try to convert and try to write the RTL implementation of the specification, right? So this is the EDA tool I am just using just to write the duty. So our first step is just to write the duty for the comparator. The design under test duty for 4-bit comparator, right? So it will be having it will start with the module. I'm just writing comparator underscore 4-bit, that is having some variables has to be as a b, and definitely I need to take greater, less, and equal if as a flag. If these values will become 1, it means it is greater. If any of the signal is, or you can say the value is, any of the variable is having the value as 0, it means that is not done, right? Means if I'm writing greater 1, less, and equal 0, it means it is a greater than, a is greater than b, right? Just define them as input. So as this is of your 4 bits, so I am just defining a vector 3 down to 0, a and b. It means now a and b both can be represented into the 4-bit. Output we have to take, as I'm just writing my code in behavioral style of the modeling. So I'm just writing greater, less, and equal. These are the three outputs are there. Just do develop the logic. So always at the rate, you have to write the sensitivity list. So I am adding all the inputs by default. Begin. Let's check first condition. Let's say a is my greater than b. So what thing you have to write? Begin. What value you need to assign? The greater will become 1, less will become 0, and equal will become again 0, right? And else, if again you have to check if a is equals to let's say b, if it is there, then greater has to be written as 0, less has to be written as 0, and yes, there are the multiple statements, so they have to be bound between begin and end. Just do remember them. So it will be 0, and definitely the equal which you are writing, equal is having the value as a 1, and then else again, else there is no need to take the third condition, because either it will be greater or either it will be equal, and if the last case will be there, then we can just directly do write it that greater is having the value as 0, uh, less is having the value as 1, less is equals to 1, and equal will also equals to 0, then end. And one more end is there which you have used in the always and end module, right? So this is the dut which you have thought about. Now let's say you have just implemented the RTL, so just run it to check the error, that either we are getting the compilation error, means some synthetical error or not, right? So yeah, there is no you can say any synthetical error. So now we will go for the verification of this, right? In the verification of that, we have to just do write the test bench, right? So this is the window where you will be writing the test bench, or the VIP, the verification of the intellectual property, means the hardware which you have thought about, you have to verify that. So test bench, how it is going to verify module, let's say test I'm just taking. I will just do take the variables over here, right? So whatever the input I just have taken, I'll just do make them as reg type, because ultimately I have to assign the values to them inside the procedural block. So I'm just taking it as capital one, and wire I'm just taking it as greater, less, and equal, right? After this you have to go with the DUT instantiation. So I will just copy this as it is and paste it here. That is the instancing of the DUT. I'm just writing one instance name that is mandatory over here, and definitely the signal which you have taken here is as capital A and capital B. So that will be written. That's greater, less, and equal. They are on the same page. So I'll just do write them as it is. Right now, the first task we have to just do right, as I told you in the here, the task to apply the input. Yeah. So let's see this task. Task one, to apply the inputs, right? So I'm just using the task is basically a kind of subroutine, right? Once you have written it that you have to pass the argument only, it will work on that, and it will come back to the main program again and again. You do not need to write the values, you do not need to write the particular instructions which you have involved in the task, right? So task to apply the input. So let's say I'm just taking the input as 3 down to 0, because we have to take it in same size, and these input as A and B, right? So begin initially only, what I can just do, I will assign them to the original inputs. So B will get it as the B of that, and A will get the A of that. Means once you are doing apply input and you are passing the input, so they will come as small a and small b. So these has to be given to original output, original input, that is capital A and capital B, and that will be furthermore driven to the, you can say, A and B of the DUT. And after each values you have to give some delay as well as, right? So end, and then you have to just simply end task, right? This is the first task to be done. Then the second one, if I'll just talk about, then we have to just display the test. So task second, just display the just just display the test, right? Means the tests are there that you have to display. So the task I'm just writing here, and given the name as, let's say, display test, display underscore test, and what values I have to display so that we can just see it. Let's say begin, I'm just using dollar display. So in each, you can say the test cases, let's divide that by using some dot, right? So first I'm just passing this message so it will be clearly visible. Then let's say I'm just displaying the values of A and B. So I have to just capture the time as well as, means the simulation time, at what time the value, the test cases is given to them, and we are capturing the output. So this is to be captured, then A is to be captured in percentage D, then B is to be captured in percentage D, and these all are belongs to the first one, the simulation which you have taken, that is for the dollar time, which is simply used to capture the simulation time. Then the percentage D is belongs to the variable which you have taken as A, and another one is to be B, right? And then what you are doing, you are also displaying the greater than, equal, and less than 2. So one more display I have to use. In that I have to represent, let's say, G stand for the greater than, so in percentage B, then L stand for less than, percentage B, and E stand for equal in percentage B, and they all are related to the greater. The second one is to be less, and third one is belongs to the equal. right? So these are the three messages. I'm just displaying this, then I'm just doing end and end task. So two tasks are done. Now we will just take the third task. What is the third task to be done? Check result. Yes. Now what we will do? We will just do check the result, and we will try to compare it with the expected one. है ना? So the third task is to be check the result. Task 3 is to check the result. So I'm just simply doing, let's say, the task, and name I'm just giving it as check underscore result. So what we need to check? So first we have to take some variables which are representing the expected greater value, expected less value, and expected equal value, and then we will try to uh, uh, capture or compare these with the original greater, less, or equal value. So I'm just taking three intermediate signal here. Let's say reg. I'm just taking it expected greater. I'm just taking it expected less, and I'm just taking it as expected equal, right? These three signals I just have taken. Then you have to write the logic that if begin, if my the value a which you have taken, if it is greater than b, I'm just making it automated now, right? So we should know it that the expected greater which you have taken, that will become as 1, and the expected less will become 0 here, and expected equal will become 0 here. And I can just do copy this and write the second statement, that else if, I'll just do take it if capital A is equals to B, the logical equality I'm just using this. So you can just copy it, paste it here. If they are equal, then this should be 1, and this two should be as 0, right? And in the else one, there is no need to write the condition. You just do write this one, copy this, and I can just do write it here, that equal will become 0. Means third possible case is what? That a is less than 1. Is it fine? Is there any problem till yet? Means are you understanding the flow, that what I am doing? Please acknowledge.
Yes, it is.
Yeah. Now let's continue. In that only we write this self, you can say the detecting thing. So let's say I just use one if. Now what I have to check, that if greater and expected greater is same, if expected less and the original less is same, if expected equal and the original equal is same, in that case the test case will be passed, otherwise the test case will be fail. The simple concept is that. So what logic I have to just draw? Let's say I'm just writing here, let's say the greater which you are generating is equal to expected greater, right? And then I'm just writing the logical end to just check the condition. So in the another one I can just do, right, the less is equals to expected less, and then again you can use the condition, the equal is must be uh, equals to expected equal, right? Mm, equal. Okay. And if this condition is true, what we have to do, we have to just simply display one message that begin, I'm just writing the dollar display, the test case is test case which you have applied, that is pass, right? This message I can print. And in else one, what we can just do, write it here, the, and in else part I can just do, right, if it is not possible, means it is just giving the 0 as the result, Then I can just simply do write it, the test dollar display, the test is fail, right? And that's it, right? So this is the you can say the, we can just do right begin, although that is not needed, we are only writing one assignment, and then one more end is there that we have used upper one, and then definitely end task, right? So this is the task which we have result to just check the result. So this was, I guess, third one, task to just check the result, that whether you are getting the expected or not. So it's a kind of scoreboard development, right? And then what we can do, we can just check the task 4, just single test case, that how the single test case can be run, right? So in that I am just simply taking let's say I just take it as name as run underscore test. In that I am just taking one variable is to be as same size, that is 3 down to 0, that is having a and b, right? And we have to inside that, whatever the three tasks we just have taken, the first one name is, I will call them all. The first one is apply input. Okay, it should be written as apply input, and then display test and check results. So begin, first I am just using apply input, and in that I will just pass the argument as a and b, means the value which I have just taken over here. Then display test we need to see, display underscore test, and then I can just check the result. So check underscore result, right? This is the single test case, right? Which we are in the inside that I am just calling the all above task which I have just written. Then end and end task, right? Every task has to be start with this task keyword, and it has to be ended with the end one, right? So this is, we have just checked it for only one test case, but we have to apply the random values, right? So the task 5 is supposed to be the random test. In random test, what you can just do, that we can just take the task, let's say I'm just doing random underscore test. uh, we are just simply begin with, let's say I would like to check with the let's say 20 loops, 20 different values I would like to give, right? So I can just do begin, and I will just call this run test, run underscore test, and inside the argument I'm just passing the dollar random and one more dollar random. So what they will do, the a value which you have taken over here, it will get some random value, b also will get some random value, and they will be coming over here. Now that the random value which you have taken, that will be given to the apply input, means it will be applied to the original inputs. Then it will go with the display test, it will displaying the test, and then it will check the result whether you are getting it correct or not, right? So this is the randomized, you may call it the verification. So the random test cases we are giving, and and then you can use the end task. This is the task 5, and the last one is just too simple, we have to print the summary of that. So last one is for this printing the summary, printing the summary, that how many test cases you have just taken and how many of them are passed, how many of them are failed, right? So I can just do write task, let's say give the same name, print underscore summary, the similarity should be there, right? So it will easier to fix the bug once you are getting during the compilation one, right? Begin. So let's say I just display one message at the end, display the simulation done, simulation result completed, simulation completed, that will be the correct. And here are your results, this message I am just passing it. And then what we can just do, print, uh, yes, we have to just now we have to just take the total pass cases and pass test and total fail test. So what we can do it here, we can just take one more variable to be taken as reg type or integer type, because the total 20 test cases you are applying, so that may be uh, store the numbers in the pass test, and another I am just taking it as fail test, fail underscore test, or count. I will use the word pass count, what exactly the pass count is, and another one is fail count, fail underscore count. And once we are applying the single test case now, in the random test case we can just use it for single test case only, or in the result one only better. Here, if the test case is passed, then in that only I can just do it that pass count will be increased, pass underscore count will be increased to as pass underscore count plus one, right? And if the test case fails, then you have to just do right fail underscore count. It should be increment in done the increment as fail underscore count plus one, right? And then what we can do here, once we are writing this now, then in the display summary we can just do represent the value of them. So to display, we can just do write it total passed test is equals to percentage d, and that belongs to the uh, percentage d, and just take the total failed test as well as failed test is equals to percentage d, and this belong to first one is pass count, pass underscore count, and second one is fail underscore count, right? This we are printing, then we are doing and task, and and task you can just do it, right? This we have done. Now it's a simple thing. Initial, all the task has been done. Begin, you can just call the random test first. That random test I am just calling. So the task which is just showing the random test, that is here in the fifth number. In fifth number only the fourth number will be called, and in fourth number all the previous three tasks will be called, right? And in the end of that I can just do write the print summary, print underscore summary. That's it. That's a kind of the automated verification. So begin and end module. I'll just run this code uh, to just check the compilation error first. So once it is running, then it will definitely give you the compilation error. It's bigger code. So yes, test bench line number 41. Test bench line number 41. I should go there. 41, 41. Okay, we have just taken it as begin. So, as I told you, it's a kind of grammatical check. The compilation means you are just checking them, that are they grammatically equal or not. Then line number 58 towards the test bench only. 58, 58. Okay, we have not assigned the value here, so it should be equal to 0. Run it again. Line number 65, 65, 65, 65. Okay, here the semicolon is missing. Okay, apply input A and B. What is the problem with that? Line number 81. Line number 81. This is not the problem. Apply underscore input. What exactly the error it is? Syntax has this error, so let me check it. Okay, let's do run this. And pass underscore count has not been declared, so let me do check it what we have written it. In line number 64, pass underscore, okay, COUT we have just written it. It should be count, right? Let's run. Okay, so it is giving the as x because we have taken the value as integer one. So integer is having by default value as x. So it is again doing the increment in that. So either you can take it as int. Int means two-state data type. So the value will become zero, and it will be just start from the zero. Either you can just initialize this pass count and the fail count with the zero one, right? Now check it out. So total passed cases are 20 and total failed case tests are 0. Let's do check it from the starting one. The time at 10, we have just given a is equals to 4, b is equals to 1. So it is greater than, so it is giving correct. Then 20 and 9 and 3. So this is greater than, giving correct. Now a and b is taken as 13 and 13. It is equal to, it is giving correct. Greater is also correct. Here less than is also correct, right? And at every point of the time we are getting the test pass, so we do not need to manually go with the all test cases, and we do not need to check it manually that what exactly is happening, right? So we can just check the in as I told you now that regression will be done in the night. They will be applying the multiple test cases, the dut is running, and then it is just simply generating the report over here. The engineer will come in the morning, they will just check this summary, and wherever the test cases are failed, they will work on that. So this is to be something known as the automated verification of the dut, right? So nowadays and in real you can say the industry work, the people are developing such kind of the vips which are uh, doing the verification on the automated base, and giving the summary at the end. And every time the engineers will try to make it bug free, either it is dut bug, either it is verification bug. Once it is completely bug free, you are getting the coverage as more than 90%, 100%, then it will be simply sent to the you can say the sign off, and means it will be sent to the sign off from the front end one, and it will be sent to the pd. You can say the people, they will be doing placement and the routing, and they are just simply verifying this, right? So I just given you the glimpse of the automated verification, and as well as how we are designing the DUT, and we have gone through this complete webinar. Now, in the end, definitely, what are the career roadmaps and what are the learning path and the key takeaways from this session, right? So uh, these are the VLSI, you can see the fundamental roles, the RTL design engineer, which is simply writing the synthesizable Verilog code for the A6 and FPGA, right? The verification people, they should have the knowledge of the system Verilog and UVM. They are making or building the test benches, which is completely of automated, and reusable facilities should be there, right? FPGA engineers who are prototype has to be taken on the FPGA, and they have to verify this. And ASIC design engineer on chip, on full chip implementation from RTL to the GTSI, right? So in that, if you will see, these are the steps, like just make the RTL as the foundation, then learn the you can say the verify and master the flow, and keep learning these all modules which I told you at every point of the time, right? These are the basic fundamentals you should know: digital system design, then Verilog HDL to make some RTL projects, then develop some test benches by using the system Verilog. Just do write the assertions and coverage of functional coverage of the system Verilog or UVM based test bench. Then definitely the UVM, that is the standard methodology that is used by the industry people uh, to verify the particular design, right, or the DUT, right? So these all will help you in you can say making your career in or cracking any kind of the interview in the semiconductor domain. Yeah. So that's all from today's webinar and the session. I'll keep myself open and listen the feedback from you people, or any kind of the doubt or questions if you would have, then I will be happy to answer. Please.
Sir, can you share the TDA playground in the chat?
Uh, you want to see this EDA playground?
Sir, actually, can you share that the one you have created now?
This code you wanted.
Ah, yes, sir.
Okay, so let me save it somewhere. Here only. Yes. So the questions.
Thank
Yes.
thank you so much, sir.
Yeah. Thank you, Anusha. So we can use the initial begin and test bench, right? What is the difference between task and the initial block? See, task is something to be called as the procedural block, and initial and always these are also a procedural block, but initial is to be called as non-synthesizable, and task is also non-synthesizable. Initial block means which can run one time, right? And we never want to make any kind of the hardware which will be running one time. That's why initial block is a kind of non-synthesizable construct, and we are using towards test bench side more. And in task, basically, this is also non-synthesizable one. The reason is that we can add the delays and all in that, and delays are basically the non-synthesizable things, right? So they should not never be used towards the DUT side. Instead of the task, you can use the functions towards the DUT. Rana Sidhu Maka. I hope you got your answer. Yes. Can you share the EDA playground? Yeah, that is done. Space. Okay. You were telling, I guess, that the error. Okay, sir, can we use the same question? Okay, is there anyone is having any queries? Okay, so thank you. I'm winding it up, and at the end I'm just sending one post to you. Let's do take the link of that. This is the post link. So I would love to see the feedback of this session from you people. Just please do uh, write your comment over there, and so it can reach to the many people, right? Those who are eager to learn, and they want to make their career, and they want to take the glimpse of the RTL codes, and you can say the semiconductor industry work, right? So I'm really happy, and really thankful to you that you have heard and listened it, uh, or shown your keen interest in understanding this RTL design and automated verification, right? Thank you for attending this webinar. Please go over there. There you will get my profile link, as well as kindly do connect, right? Thank you. Take care. Have a good day.